How are algorithms used in AI? Well, let's have a look at the uninformed search algorithms. There are 5 main algorithms, so we'll have a reminder of how they work, and then we'll use a simple example to show why use that algorithm. That hopefully will help us understand all the technical details. So uninformed means they explore a search space systematically, but they don't have prior knowledge, so they rely on a basic strategy. So uninformed v informed, really, without knowledge and more time consuming and complex. So let's have a look briefly at what the 5 algorithms are. Breadth first search, we cover each level, we go down a tree or we go through a graph using all the nodes in each level. Now depth first search is different. We go down as deep as we can. So in this example we would go 1, 2, 4, 5. So you can see that all the nodes in the first half would be visited before the nodes in the second half. So that's a different approach. Again with the graph, we'd follow through the depth, the deepest roots, and then go through the tree. Depth limited search, as you can imagine, very similar to the depth first search, except we have a limit. So here the limit is 2, so you can see we go through each level using the depth first search approach, but it's limited to the depth that it goes. Here's another example with the limit at 3. You can see we still go through the nodes, and even if a graph, we go through here to just level 2, the same approach as the depth first search, but with a limit on the depth. You can see with the iterative deepening search that we have a limit, and we use the depth first search approach to get the nodes up until that limit. The iterative part is that we start again on each depth, on each level. So in the graph example you can see clearly we start at 1, then 1, 2, 5, 3, then 1, 2, 4, 7, 5, 3. We go back to the root node each time we iteratively go through the graph or tree. In some trees and graphs there's a cost going from one node to another. Now this is where we use the uniform cost search. Here we go through each node working out the cheapest and least cost path going to that node, whichever path that it takes through other nodes. And it's the same for the graph. Now let's get to really understand these algorithms with a clear example. The breadth first search. Here's an example of a small town, and we want to get to our neighbour's house. So from S to E. Now there's different junctions. Now which route shall we go? Now with the breadth first search we'll find the quickest route very quickly, because we don't go through any long routes, we just try the shortest routes closer to our home. So in this example the breadth first search is a good approach to this problem. We'll get the answer. Now what about the other algorithms? Why can't they do this? Well, the depth first search, for example, has to look at the first half before the second half. So we'd go through a lot of trials and errors of different paths and long routes before we get to someone's house if it was on the second half of our search. So that's not very efficient. Limited, we might not even find the house. Iterative deepening, well, we'll keep going to pretty much every junction. So if it's far away, we're going to be pretty exhausted by our search by the time it finds it. And uniform cost search, a bit overkill. We don't really need to have a cost to finding our neighbour's house. So the breadth first search, quite simple implementation. It finds the shortest path, quite efficient, no long paths, no long detours. And its uses, well, this can be used for social network connections, flight paths and web crawling, indexing pages, so we make sure we get the index of the shortest path. So that's how we can use the breadth first search. Now the depth first search. Here we've got some caves. Now when we go down the caves, we need to make sure that we check every part. So we go down each level and then we check right to the end of each level and each position in each cave to make sure we find what we're looking for. So in this case, the depth first search algorithm will do what we want. What about the others? Well, with a breadth first search, we would go through some routes without getting to the end, then backtrack to go down a different route. So that's not what we want. The depth limited search, we might not find what we want. And also the iterative deepening search. Again, similar to the previous two put together. Again, with backtracking and not finding what we want. And there's no real need to try to add a cost in this example. So the depth first search is quite simple. It's memory efficient compared to other algorithms. We can get through to the deep paths and detect dead ends. And also it can be used for things like chess, for example, exploring the different moves, or a jigsaw puzzle, or Rubik's Cube. So you can explore different combinations deeply to get the answer that you're looking for. So that's the depth first search. The depth limited search. Here we've got layers underground that have different levels of poisonous gas. And you can see the darker the grey, the more poisonous gas. So we can state that we can go down, let's say, 3 levels quite safely, and then after that, not so good. Here we've got squares illustrating areas where we need to go to. Now we can go through these in different orders, but the main thing is that we don't want to go deeper than the safest level. So in this case, we want a depth limited search. The breadth first search, well, it's going to go through everything on each level, but potentially it will actually go down too deep from what we want. Depth first search will do that even quickly. It will just go through the first option that goes under the level that we want. So that's not good. And iterative deepening search, very similar to the breadth first search in this case. So the depth limited search, simple to implement. It's resource efficient, won't explore like deep paths like the depth first search, as you have more control on what depth you go to. So you can use it for things like solving Sudoku puzzles, suggesting movies in a specific genre, and also route planning. Let's say you've got some restrictions on what region you can cover, for example. So similar to the depth first search, but because you can control boundaries and limits and levels, there are more benefits. Iterative deepening search. Now here we've got a maze. To find the solution, we can go through all of the options. So in this way, we go from the start, we try something. It's no good, we go from the start, we try something else. And we do that in the order of quickness, if you like. So shallow options first, and then go to deeper options, which is exactly what this algorithm does. So we can do that quite simply. Now the other algorithms, well, a breadth first search will just go through every option in our maze at the beginning, then the next level, then the next level. So that's going through every option without really trying to find the answer. So when we look at our maze, it will go through each node and then stop and go back to the next node rather than trying to find the solution. The depth first search will just keep going into deep branches, and it might not even find the solution in the end. The depth limited search, well, that might not even find the answer, and it could become very expensive because it's looking through so many nodes. And we don't really have any cost, so the uniform cost search is just wasting memory. So the iterative deepening search, suitable if you don't really know like the depth of a problem. So you want to start off shallow and go in iteratively deeper depths. It will find the shallowest solution without consuming too much memory. You could look at shortest sequences of moves in a chess puzzle to find checkmate, or perhaps find the best moves in some games. And if you want to allocate resources, you might try different options, starting off from the least expensive and then go through the options to find what you want the resources to be able to be used using this iterative deepening search. Finally, uniform cost search. Well, here we associate a cost with the travel from one node to another. So let's say, for example, we want to go from node 1 to node 4 here. Now we can quite simply look at the cheapest route from 1 to 2 or 3 is 2, 2 to 3 or 4 is 3, and then 3 to 4. So we calculate the cost from our original node to our target. In this case, the answer is 60. So from 1 to 2 to 3 to 4 is 60. Now, the other algorithms won't really be able to do this because they don't look at the costs. And also they might find an incorrect answer. So that might happen with the breadth first search. It could also happen with the depth first or depth limited searches and the iterative deepening search. They won't find the solution and they might not even find the lowest cost. So that's quite unique because this example we have this cost related to the different paths. So we can take in different types of cost into this algorithm, and even if there's a trade-off between time and cost, we can allocate that inside the algorithm and it will find the lowest cost path without too much memory. So this algorithm, we can find the most energy efficient route for a robot, the most efficient cost-effective plan in distribution, or lowest response time for an emergency responders, while they might be influenced by like traffic jams or traffic lights, etc. So whether there's some type of cost involved, we can use the uniform cost search algorithm. Well, I hope you enjoyed those examples. We'll move on to the technical details, but I think that's enough for this video. So we'll make a second video that describes all the technical details of the uninformed search algorithms. That will be part 2. So join us soon for that.